LearningMeasure.tv. Science and engineering podcast with emphasis on measurement. Brought to you by David Archer and LearningMeasure.com. Episode -1. Noise in the Cosmos, Part 2. Hello. Welcome to episode -1. I'm sorry about this being late again. It's like I'm trying to get these out weekly, but it seems that we're getting them out every other week. But we're still trying for a weekly thing here. One of the things I'd like to announce, if you look on the website LearningMeasure.tv, there's now a link in the right-hand side of the screen, and you scroll down a little bit. There's a link that says free publications. If you go down there and click, and you can register for literally hundreds of free trade publications if you're interested, and that will help support this podcast. Also, I want to make a little announcement. We've just added a course, Measurement 106 SI Units, the Kelvin, to our course catalog at LearningMeasure.com. And we're actually put it in the course catalog to get some feedback to help us finish the course. So if you're an expert in temperature measurements, we'd love to have you look at that. Okay. This is part 2 of, oh, by the way, I'm David Archer. I forgot to mention that. This is my podcast, and I'm also the owner of LearningMeasure.com. Training and consulting website. Last week we talked about basic noise measurements, and in particular we talked about the definition of noise temperature. Noise temperature being, it's the power per unit bandwidth divided by Boltzmann constant. And it's a function of frequency. Okay, then we talked about a way to measure noise, a noise measurement system where we have a switch and a receiver that measures power of some sort. And then from that, you can have 3 noise sources. 2 of them are standards, a cold standard, a hot standard, and the unknown you're trying to measure. So T cold, T hot, T unknown. And we talked about you can measure the power rate there, and there's also a TS associated with the whole system, the system noise temperature. The Y-factor method for measuring noise is you switch between the hot and cold first. The ratio of the powers, which is the ratio of the power hot, ratio of power cold measured, which equals the hot temperature, hot noise temperature plus the system noise temperature over the cold temperature plus the system noise temperature. Well, then you can do the same measurements between the cold standard and the unknown temperature. So again, it's the P unknown over P cold, which is equal to T unknown plus TS over TC plus TS. And from that, you can solve for the system noise temperature. TS equals T hot minus Y hot cold, T cold over Y hot cold minus 1, which then you can substitute back into here and solve for TU, and you end up with what the measurement equation for this setup is Y unknown cold, T cold, plus Y unknown cold minus 1 over Y hot cold minus 1 times T hot minus Y hot cold T cold. Now this particular measurement equation doesn't include things like mismatch errors, losses in the switch, losses in the transmission paths, extra noise generated by the different transmission paths. Those terms would have to be added in a more complete measurement equation, but this gets the basic idea. Okay. And then we talked about, well, if you take this unknown and you put oh, it's the wrong kind of pen. Anyway, you take this unknown and you replace it with a antenna, and you could do radio astronomy. Well, before we go into what that, last week we got a little cosmology lesson. We're just going to add to that this week. Okay, now once you've established that there's this cosmic microwave background that is consistent with the Big Bang, the next question you might want to ask, is it uniform? The reason why is in order for stars and galaxies to form, it must not be uniform. In fact, there has to be a certain amount of anisotropy, which is a fancy word for lumpiness, in the matter in the early universe, or else the galaxies won't collapse. You know, stars and galaxies won't collapse. So it would be nice to be able to look at these, look at this background radiation, and see if there is lumpiness to it. If there isn't, there's a problem. There's a problem with our model. So once you've actually established that you have a cosmic microwave background, the next step is to figure out how lumpy it is. And after that, if it's lumpy enough to be consistent with galaxies and stars forming, which we know happened at some point. Okay, so satellites what have been used to measure the anisotropy in the cosmic microwave background. And in fact, a lot of this information, most of the information that we're going to talk about for the rest of this episode is on, can be found on the website lambda.gsfc.nasa.gov. So in the next little bit, we're going to talk about the COBE satellite. COBE stands for Cosmic Background Explorer. It had 3 instruments on it: the diffuse infrared background experiments called DIRBY, far infrared absolute spectrometer FIRAS, and the differential microwave radiometer DMR. This is what we want to discuss in this episode, because hey, that's what this is. It's a differential microwave radiometer. Okay. What you should see now is a picture of what the DMR instrument looked like before it was assembled. If you look, you'll see there's 2 antennas at the top pointing at 60 degrees from each other. So this thing mapped the sky with 2 antennas pointing 60 degrees apart. And there's also at the bottom, you can see a switch, and that switched between the 2 antennas and noise sources that were used to calibrate the thing. If you look at this next image here, you can see basically the schematic diagram of what the receiver looked like. 2 antennas connected to a switch, and you can see the 2 things marked calibrator on this drawing are the noise sources used to calibrate it. And then there's a mixer to down convert, an amplifier, and a detector. And then they have this synchronous demodulator switch so that they can, well, you need to measure the ratio. You have to know when you're measuring and where the switch is. They have to be synchronized. Okay, this is basically no different than what we showed you on the board so far. And then here's an image of the satellite assembled. Now you notice that there's a shield, it looks like a cone, that is used to block picking up microwave emissions from the ground and from the sun. That then again, you might wonder, how come it doesn't ever point at the sun? You know, you'd think that it would be really hard not to point at the sun or the ground, because if it was like between the ground and the Earth is a bright microwave source, and you don't want to look at that either. Well, the way you do it is the orbit. If you look at this picture here, it's in a special orbit called a sun-synchronous orbit. The thing as it rotates around the Earth in almost a polar orbit, it's always pointing away from the Earth. And the plane of the orbit is at right angles to the sun. Now the orbit's been arranged so that it precesses, in other words, the whole orbit rotates one rotation per year, which means that by doing that, the satellite will never point at the sun as long as they can keep it in that orbit. Okay, so then the other thing you might want to wonder about is, well, how do you keep it from pointing at the moon? Well, you don't. With something like this, whenever the moon comes into view, it can be used as another calibration source to make sure that you got the accuracy out of your instrument. Okay. So once you have this, it rotates, 360 degrees around the Earth, and it rotates about its axis every 8 minutes. So it's doing essentially circles, measuring circles around the sky. This entire sky can be mapped every 6 months with this configuration. And the observations that were made over a 4-year period. Now, the images you're seeing now are the results of the measurement. The top map, there's 3 maps that you're seeing right now. The top map shows the raw data, basically. And you notice that it sort of looks like there's 2 parts to it. Well, this can be explained by what we were talking about last week in the Doppler shift, because the Earth is moving through space, so it's moving with respect to whatever the cosmic microwave background is. So in one direction it's red shifted, and 180 degrees from that it's blue shifted. Well, fortunately, it's fairly straightforward to remove the effect of Doppler shift from the data, and that's what the middle image is. That was after, you can start to see some lumpiness, but you see a band in the middle of that. Well, that's due to our galaxy. So the next step is, which is a lot harder, is to remove the galaxy from the image. But it is doable, and they knew how to do it, and they did. So the third image that you see on the bottom is the result. Now, this is a nice image in that it basically shows what they're trying to do. And it does show lumpiness. Now, what this doesn't tell you is the lumpiness is in the background radiation is something like a factor of 1 in 100,000. So it's not much contrast there, but it's there. It's nice to visualize that, but what they actually, one of the more important things is they're able to show through their uncertainty analysis and their measurements that they were able to show a lower bound of the lumpiness. In other words, it is lumpy. And the people involved with this, Dr. John Mather and Dr. George Smoot, received the Nobel Prize in Physics in 2006 for this work, which is pretty good. I mean, so far, noise measurements have resulted in 2 Nobel Prizes. How's that? Well, now I want to talk to you a little bit about a follow-on experiment that is the WMAP satellite. WMAP stands for Wilkinson Microwave Anisotropy Probe. It was designed to be a more accurate and higher resolution instrument than COBE to get the more, like I said, more detailed measurements. One of the unique things about this satellite is its orbit. Again, instead of a sun-synchronous orbit, they sent this satellite to what's called the L2 point, stable point in the Earth-Sun system. You put a satellite there, it tends to stay there. It's such an orbit that the Sun and the Earth are always the same direction from the satellite, so you could shield them better, which is kind of interesting. And then here's a picture of the map. As you can see, it's significantly more detailed than the COBE image. Well, this was produced by the WMAP science team. It can be found on the site that we mentioned earlier. Okay, that pretty much covers it for this week. Next week, episode 0 will be basically a meta episode. What we plan on doing on episode 0 is basically explaining what we're trying to do here at learningmeasure.com and Learning Measure TV, and what our plans for the future are. So, again, if you like to support this podcast, we ask that you now go down to and you're interested in getting some free trade publications, go to learningmeasure.tv site, and on the right-hand side towards the bottom, there's a link that says free publications. Check them out. That'll help support the podcast. Okay, and like I said, always if you're a vendor who are wanting to demonstrate your measurement-related products here, we'd love to have you, or if you were interested in sponsoring us, we'd love to have you. Just send us an email at vendors@learningmeasure.tv. And if you have any suggestions, comments, questions, in fact, if you have a measurement-related question you'd like to see answered on the podcast, we'd love that too. Send that to suggestions@learningmeasure.tv. Also, if you'd like to join our consultant network, follow directions on the learningmeasure.com website, and we could give you an interview here. Or if you're in the Las Vegas area and you're interested in getting on the podcast for an interview or something, to demonstrate something or to talk about whatever it is you're doing, also give us an email at suggestions@learningmeasure.tv. That's pretty much it. We'll see you next week, or well, I can't promise next week, but see you on the next episode. Okay, goodbye.